Starting. All attendees are in listen-only mode.
Welcome, everyone. My name is Tracy Fitzpatrick, and I'll be your moderator today. Thank you so much for joining us here at Netcom Learning, a market leader in promoting lifelong learning, training, and talent development solutions. We're very excited to host today's webinar, An Introduction to Software-Defined Networking, SDN Part 1. Presenting today's topic is Robert Piper. Robert is a Cisco certified subject matter expert with over 34 years of experience in the information technology industry. He has provided corporate trainings, including hands-on and virtual practice labs featuring the latest Cisco equipment in real-world relevant scenarios to help professionals prepare for real networking environments and Cisco certification exams. Now, please bear in mind that this is an overview of a very robust topic. We do offer a collection of technical and business courses that can be tailored towards your specific requirements. If you are interested in a further discussion, you can make an appointment with our learning consultants through our website at netcomlearning.com. Today's session is also being recorded, so you will get access to the recording in the next 24 hours via email. Netcom Learning helps customers build innovative learning organizations by achieving a smarter workforce, adapting to change, and driving growth. We do this with a broad catalog of offerings, developing customized learning plans, and our global delivery capabilities. Since 1998, we've been empowering organizations with our managed learning services to help them reach optimal performance results and address challenges. We do have 9 practice areas in which we specialize. They encompass people, process, and technology training. Today's presentation will be from the networking practice area. Netcom Learning offers a comprehensive training portfolio for networking courses as well. And here's a list of our upcoming classes on our public schedule, which you can see right up there on your screens. On June 26th, we're offering Interconnecting Cisco Networking Devices Part 1. And then followed by Part 2 on July 30th. We're also offering networking with Windows Server 2016 on July 23rd. Implementing Cisco IP routing will be held on June 11th. And finally, Data Center Application Centric Infrastructure Fundamentals will be on July 9th. We can also deliver private training to teams, of which the learning plan can be customized to the specific needs of that audience. These offerings can also be found with a simple search on our website at netcomlearning.com. So why should you attend this webinar? Netcom Learning presents an important installment in An Introduction to Software-Defined Networking, SDN Part 1. In this webinar, we will illustrate the concept of SDN and how it has shaped computer networking with real-time scenarios. The webinar not only helps us in understanding what is OpenFlow, but also talks about the skills required to master SDN. Now, I'd like to give you a quick overview of the logistics before we get started. To begin with, you do have the option to adjust the window size to your liking. Simply hit the Escape key and find the Zoom button on the top left corner of your GoToWebinar viewer. Everyone has been muted except for our presenters. Please feel free to submit any questions you have for the presenters here in the questions pane, and we will address them at the end of the session. A PDF copy of today's slides are also in the handout section of your GoToWebinar viewer. And now I'm going to pass this over to Robert, who will be presenting today's topic. Go ahead, Robert, you're live.
Great. Thank you very much, Tracy. Appreciate it. Just want to make sure everybody can see that screen okay. And before we get started, I'd like to ask a question just to kind of get a feel for the audience here. If you would, just give me something into chat to tell me what your role is. Are you a network administrator? Are you a network engineer? Just so I kind of know who I'm talking to. We'll give you guys a couple of minutes to type that in there before we get started. And I just wanted to say that it's my pleasure to join you guys this afternoon and give you an introduction to SDN. And we're going, like Tracy mentioned, we're going to try to give you an overview. We're going to talk. We're going to give it to you conceptually. We're going to have some details, and we're going to try to keep it as a general overview and not get into the bits and bytes of things too much. We're also at the end, we'll talk about what we're going to do in terms of Part 2 in about another 10 or 12 days or so. All right, good. Well, we'll go ahead and we'll get started.
Okay, Robert, I'm going to jump in because you can't see what they're writing, but we have people starting real estate company, network engineer, network management architect, telecom consultant, etc. So those are the responses you're getting.
All right, good. I was wondering why I couldn't see that. All right, good. Well, that's excellent. Let's go ahead and get started then. Here's our agenda for this afternoon. We're going to give you an introduction of software-defined networking, or SDN. We're going to give you an overview of the architecture that's included as part of software-defined networking. We're going to actually discuss what is OpenFlow. There's some confusion with regard to, is OpenFlow SDN or is SDN OpenFlow, but we're going to compare and contrast OpenFlow as it relates to the SDN architecture. Then we're going to talk briefly about Cisco's application-centric infrastructure. And we're going to end our discussion this afternoon by talking about what are the skills that you need as a network professional in order to be prepared for or be engaged with some SDN projects out there. And then we'll open it up for a little Q&A after that as well. So to get us started, let's talk about SDN, where that term kind of came from, because over the past few years, it's been a key buzz phrase, right? So what is SDN? We'll read this real quick and then we'll talk about this in a little bit more detail. SDN is actually a framework that allows you and I as network admins to automagically and dynamically control and manage all of our infrastructure devices, including services, topology, traffic paths, QoS, how we handle packets, using high-level languages as well as APIs or application programming interfaces. We'll talk about that as well. Management of SDN includes the provisioning, monitoring, optimizing, and managing the fault configuration, accounting, and performance, as well as security in a multi-tenant environment or a data center. So we've heard that term, right? That's why we're here on the call this afternoon, because it's been a key buzz phrase inside of the IT world, because more and more companies are discussing how SDN might fit into their future plans. And they're trying to figure out how to leverage it for their business and future growth. Why? One of the primary reasons is that SDN reduces capital expenses of network equipment, as well as the operational and maintenance expenses of a corporate network. So that's the primary reason why every business in the networking industry wants at the end of the day. So what's so special about software-defined networking that your existing or legacy networking is not able to deliver? Well, we're going to talk about that. We're going to talk about how traditional networks can't cope and meet the current networking requirements, things like dynamic scalability, central control and management, on-the-fly changes or experiments, manual configurations on each networking device, how it handles network traffic, which we all know has increased due to the boom of mobile data. We've got server virtualization traffic in our data centers now. And what's more, our traditional networks are tightly coupled with highly expensive elements that don't offer any kind of openness or ability to customize. So to deal with these potential issues, the open source community has come together to define a network approach for the future. And that's how the concept of software-defined networking came to life. So we're going to have to, in order to answer what SDN is and why you're hearing about it, we're going to have to take a closer look at traditional networking first. So we'll discuss how that works and the current limitations of traditional networking. And I will explain what SDN is and how SDN is supposed to solve those challenges that exist with traditional networking. So with traditional networking, we have specific infrastructure devices that include our switches and routers that are used to perform specific tasks, things that we've been very familiar with. A switch, for example, is responsible for delivering frames in the local area network, based on the destination MAC address in that frame. A router, on the other hand, has to identify the destination address that's in the packet, and it's got to determine if it has a route in its routing table to the network that that IP address resides in, and out which interface is going to forward that packet onto the next hop router. So these tasks are separated by different planes. We call these planes the control plane, the data plane, and the management plane. So we're going to take a look at the difference between these three planes. The control plane, for example, is responsible for learning and exchanging routing information with regard to a router. Some of the tasks that are performed in the control plane include learning the MAC addresses in order to build the MAC address table on a switch. The router will build ARP tables. ARP, of course, as you know, is Address Resolution Protocol. We resolve a layer 2 MAC address to a known IP address. That router makes decisions about where traffic is sent based on the destination IP address. The control plane functions include things like the system configuration, the management, as well as the exchange of routing table information. That routing controller will exchange the topology information with other routers, and it'll construct that routing table based on a routing protocol. The ones we use most likely are going to include both OSPF, EIGRP, and then from routing from one autonomous system to the other, of course, we're going to use BGP, or Border Gateway Protocol. The data plane is the actual movement of those packets over the path that we learned as part of the control plane stage. So it's this data plane that relies on the information that the control plane supplies. Some of the tasks that the data plane takes care of for us include the encapsulation and de-encapsulation of packets, adding or removing headers, like the 802.1q header, matching a MAC address for forwarding, matching an IP destination in the routing table, perhaps changing the source and destination address when using network address translation, and also dropping traffic because it doesn't meet our access control list. And then the third part of that plane is the management plane. That's typically used for access and management of our network devices. For example, accessing a device through either Telnet or Secure Shell, or even at the console level. Now, when we talk about SDN, we mentioned the control and the data plane, and that's because those are the most important to keep in mind. As you see the control plane, where we use routing protocols like OSPF and EIGRP, we also can include some static routing. We know that the best routes are going to be installed in the routing table. We mentioned briefly that another table that the router has to build is the ARP table. Information from that routing and both the ARP table are then used to build the forwarding table. So when the router receives a packet, for example, it has the ability to forward that quickly since the forwarding table has already been constructed. So everything that I've described thus far is the way that we've done things in the networking world for the last, I don't know, 25 or 30 years or so, right? So there's not like there's something wrong with traditional networking. However, we have some additional business challenges that are prompting us for different solutions. For example, let's say that we have a company or customer that has a business requirement for a new application that requires 4 new virtual machines to be installed on a VMware server, for example. For security reasons, each of those VMs should be in a different VLAN. So a typical user should be able to access the application that runs on each of these VMs. So let's take for a moment, or think about for a moment, some of the things that we would have to configure as a network administrator in order to make this happen. We've got to create the VLANs on all of our switches. We have to configure a root bridge for the new VLANs. We have to assign 4 new subnets, 1 for each of our VLANs. We need to create new virtual sub interfaces and configure IP addresses and masks on those switches. We need to configure some redundancy protocol, either VRRP or HSRP on the switches for the new VLANs. We got to configure the firewalls to permit access to those applications. We got to advertise those subnets with our routing protocol on our layer 3 switches, our routers, and also make them available through our firewalls. So even though there may exist some automation tools to help us, as admins, we've traditionally used the command line interface in order to configure all of those devices one by one. And as you know, it's a slow manual process that takes time. And while it only takes a few minutes to spin up a new virtual machine, it might take a few hours for you or I or the network team to prepare the actual network. So it's challenges like these that are typically done during a maintenance window and not during normal business hour. So things like server virtualization is one of the reasons why businesses are looking for a solution that will speed up that manual process. So before virtualization, we used to have one physical server with a single operating system. Now we have a choice. We can have multiple physical servers with hundreds of virtual machines. And these virtual machines are able to move automatically from one physical server to another. And when they cross a layer 3 boundary, you don't have to wait for the network team to make the required changes to routing or an access list. All of it should be automatic. So that's the trend. The trend is that everything should be virtual. So it's not strange to see that this is also happening to networking. So we've got large companies out there that include Cisco that used to sell only proprietary hardware that are now offering virtual routers, adaptive security appliances, wireless LAN controllers, all things that you can run on VMware servers. So let's talk about this concept, and I'll give you an analogy. Let's say that you and I are in charge of a public transportation for a small city. Before we send those bus drivers out, we need to have a plan. So it's the control plane that's going to give us that plan. The control plane is where we're going to learn what we need to do. So in our planning stage, which includes learning which paths the buses are going to take, that is similar to the control plane in our network. We haven't picked up any people yet on our bus, but we also haven't dropped them off, but we do know the paths and the stops due to our plan. So the control plane is primarily about learning the routes. In a routed network, this planning and this learning can be done through static routes, where we train the other routers about remote networks and how to get there. We can also enable and configure dynamic routing protocols like OSPF and EIGRP in order to dynamically exchange information with the routers in our autonomous system, so that we all, or I should say, so that all of the routers know how to reach remote networks. This is all done in the control plane. The data plane is where the actual moving of the packets happen based on what was learned in the control plane stage. So after the routers know how to route to the remote networks, along comes a customer packet, and then bam, that's where the data plane begins. So the data plane is the actual movement of the customer's data packets over the transit path that was identified in the control plane stage earlier. So hopefully that gives you a little bit of an analogy on how the control plane and the data plane work together. Just like the buzzword cloud a few years ago, it seems that every organization or vendor has a different opinion about what software-defined networking is, as well as the different products that they offer. So we talked briefly about how traditional networking uses a distributed model for the control plane. We talked about protocols like Address Resolution Protocol, OSPF, EIGRP, BGP, STP, for example. They run separately on each network device. And when these network devices communicate with each other, there's no central device that has an overview or that controls the entire network. One exception I'll add is, for those of you that are familiar with wireless networking, are that wireless LAN controllers, WLC. When you configure a wireless network, for example, you'll configure everything on the WLC, which controls and configures all of your access points. And that's so that we don't have to configure each access point separately. It's all done by the WLC, excuse me. So that concept has found its way into SDN, where we use a central controller for the control plane. So depending on the SDN solution that you're using, this could mean, for example, that the controller takes over the control plane 100%, or that it has insight into the control plane of all of your infrastructure devices in the network. That controller could be a physical hardware device, or it could be a VM in the cloud. So when we talk about the SDN architecture, you're looking at the three components or groups of functionality. The SDN applications are programs that communicate behaviors and resources within the controller via a API or application programming interface that we'll talk about, I believe, on the next slide. Also, the applications can build an abstract view of the network by collecting information from the controller in order to make decisions. Those apps could include things like network management. They could include analytics. They could include various business applications that are used to run large data centers. For example, you might have an analytics app that could be constructed to recognize suspicious network activity for security purposes. So that's the application layer. Then you've got the control layer, which is a logical entity that receives instructions or requirements from the application layer. And then it relays that information to the actual infrastructure components. That controller extracts information about the network from the hardware devices. It communicates back to the applications with an abstract view of the network, which might include things like statistics and events about what's happening in real time on your network. The actual infrastructure layer includes the actual devices that do the work of forwarding frames and packets throughout the network. So traditional networks would include sometimes hundreds or even thousands of devices in the forms of routers and switches that are equipped with software and networking functionality. The SDN architecture will change that paradigm by removing the intelligence from the actual infrastructure devices themselves and transferring that intelligence to a central controller that allows you and I to manage the networks through software instead of hardware. That essentially is what SDN is all about. So with SDN, we can separate the control plane of the network from the forwarding plane and automate things like provisioning, configuration, and remediation, which allows organizations from a business perspective to be more flexible, more agile, and be able to deliver applications in a much timelier fashion. So SDN offers a centralized view of the network, and it gives the SDN controller the ability to act, for lack of a better term, as the brains of your network. And that control layer of the software-defined network is usually a software solution that we refer to as the SDN controller. And by using APIs, business apps will tell that controller what they need from the network and have the network actually deliver that to them. So we mentioned API. What is API for those of you that are unaware? API stands for Application Programming Interface. We're not going to get into the details of APIs, but we're going to break it down by looking at each of its parts. So if you have a smartphone, for example, you are well acquainted with what apps are. They're the tools, the games, the social networks, and the other software that you and I use every day. Programming is how engineers create the software that make our lives easier. An interface is that boundary that's shared by two apps or programs that will allow both to communicate with one another. So in essence, an API is a way for programmers to communicate with a certain application. So every time you want to access some data from an app, you have to call the API. But there's only a certain amount of data that that app will let you access. So you've got to communicate to the operator in a very specific language. That language is going to be unique to each app. So to help visualize that conceptually, imagine that your API is the middleman between a programmer and the actual application. That middleman can accept requests, and if that request is allowed, it'll return the data. That middleman can also inform programmers about everything that they can request, exactly how to ask for it, and also how to receive it. So we already talked about how SDN, and specifically the architecture, will differ from the architecture of a traditional network. We talked about the data or the forwarding plane. We said that that contains network elements, and it deals with customer traffic. We said that the control plane represents the core layer of the SDN architecture. It contains the SDN controllers, which provide control of those devices in the data plane. And then we talked about the application plane, which contains the apps that communicate the network requirements toward the controller. And then we just spoke about how the SDN controller uses APIs in order to communicate with the application and the data plane. So the goal of software-defined networking is to enable cloud computing and network engineers and administrators to be able to respond quickly to changing business requirements via a centralized control console. So SDN originally defined an approach to designing, to building, and managing our networks that separates the control or the brains of that SDN network policy and the forwarding or the muscle planes, enabling the network control to be directly programmable and to be able to deliver network services for apps like SDN cloud computing or mobile networks. Now, SDN providers will offer a wide selection of competing architectures. But when we break it down, we said that the SDN method will basically centralize the control of our network infrastructure by separating the logic to off-device computer resources. So all of our software-defined network solutions have some version of an SDN controller, as well as what's called southbound APIs and northbound APIs. So let's talk about that. We said that the controller acts as the brains of our network. It offers a centralized view of the network and it allows you and I as network admins to dictate to the switches and routers how the forwarding plane should handle the forwarding of IP traffic. Those southbound APIs that are used in SDN are what relay information to the switches and routers below. That's why it's called southbound, below. OpenFlow, for example, which is considered the first standard in SDN, was the original southbound API, and it remains one of the most common protocols. We'll talk about that in a couple of slides. Also, SDN uses what's called northbound APIs in order to communicate with the applications and the business logic above or northbound. What that does is that helps, among other things, you and I to be able to shape traffic to meet things like QoS policies and also to deploy services. So a northbound interface is defined as a connection between the controller and the application, where the southbound interface is the connection between the controller and the actual hardware itself. And because SDN is considered a virtualized architecture, these northbound and southbound elements don't have to be physically located in the same place. And communication with the data plane is defined with those southbound interfaces, while services are offered to the application plane using those northbound interfaces. So those northbound interfaces, for example, we said are used to access the SDN controller that allow you and I to access the SDN in order to configure it and retrieve information. This could be done through a GUI, for example, but it also offers an API which allows other apps access to that SDN controller as well. You can also use scripts to automate your network administration. Other examples might include, you could create a list of information from all of your network devices in your network. You could show the status, for example, of all of your physical interfaces. You could add new VLANs on all of your switches. You could identify and display the topology of your entire network. All of this can be done using scripts. You can automatically configure your IP addresses, your routing information, your ACLs with a new when a new virtual machine is created. Your southbound APIs, which we said are device to control plane interfaces. We said that those are used to communicate between the controller and the network device. So that controller has to communicate with those devices in order to program the data plane. And that, we said, is done through that southbound interface, not a physical interface, but a software interface through an API or application programming interface. And there are a number of southbound interfaces that are out there. There's Cisco OpFlex. That's an open source protocol which has been submitted to the IETF for standardization. There's the Netcom, which is a network management protocol that's been standardized. That's been created to allow the installation, manipulation, and deletion of configuration of our different network infrastructure devices using XML. And then we've got OpenFlow, which is probably the most popular southbound interface at the moment. It's an open source protocol from the Open Networking Foundation. Now, there are quite a few networking devices and SDN controllers that support OpenFlow. And then, of course, there's also Cisco offers the CLI, or what they call APIC EM, which is an SDN solution for the existing routers and switches. We'll talk about some of this stuff in 12 days when we talk about part 2 of SDN. Just to give you another example before we're going to talk about some of the details of OpenFlow, but Netcom, for example, is a protocol that allows you to modify the configuration of a hardware device, whereas OpenFlow is a protocol that allows you to modify the forwarding table. So if you need to reconfigure a device, Netcom is a solution that you would use if you want to implement new functionality which is not necessarily configurable inside of that device. Then you should be able to modify that forwarding plane directly using OpenFlow. We'll talk a little bit more about that in the next couple of slides. So through the API, we can have multiple apps that are able to access the SDN controller. So this slide here gives us an example of a user that's using a graphical user interface in order to retrieve information about the network from the SDN controller. Now, behind the scenes, the GUI is using the API. There are scripts that have been written, for example, in Java or Python that will tell the API to retrieve information from the controller, or you can configure it to, or use it to configure the network. There are other apps that are able to access the controller. There might be an application, for example, that automatically configures the network once a new virtual machine is created on a VMware server, for example. Now, let's talk about OpenFlow. What is OpenFlow? Well, that's a communications protocol that gives access to the forwarding plane of a network switch or router over the network. So we mentioned that OpenFlow is considered one of the first SDN standards, originally defined the communication protocol that enables the SDN controller to directly interact with the forwarding plane. Remember, that forwarding plane is what is directly responsible for how those packets are going to be delivered on switches and routers, both the physical and virtual or hyper-based, so it can better adapt to changing business requirements. So we mentioned earlier that people point to OpenFlow sometimes as being synonymous with software-defined networking, but OpenFlow, in fact, is only a single element in the overall SDN architecture. So we said earlier that SDN acts as the brains of our network. It relays information to our switches and routers via those southbound APIs below, and that the applications and the logic above via those northbound APIs, So as organizations deploy more SDN networks, those controllers have been tasked with federating between different domains using common application interfaces like OpenFlow and open virtual switch database in the case of multiple data centers. So OpenFlow is a specification that's managed by the Open Networking Foundation, which defines the functions and protocols that are used to manage switches using that centralized SDN controller. So it essentially is a command and control protocol that includes communication over secure shell. It features discovery and the configuration of devices by the controller. It allows you to manage the forwarding tables on switches. It doesn't stipulate, however, how the network is designed or managed. That's up to each customer or vendor or network designer in order to decide. But OpenFlow is also designed to work with your existing products so that you don't need any specialized hardware. So there are a number of vendors out there, for example, that are offering experimental hardware that runs OpenFlow and can run both OpenFlow on their native hardware and software on the same switch by dedicating specific ports to both OpenFlow as well as the native switch. So there's a couple of vendors, I think Fujitsu and NEC, they're shipping OpenFlow switches. I think Fujitsu's switch is OpenFlow only. I think NEC's is a hybrid. The challenge with today's network, though, is how it was originally designed as a simple framing protocol. As our local area networks become more complex, we had spanning tree to remove the possibility of broadcast storms, and it reduced the way that our networks would run to a single tree so that not all of the paths could be used. Also, QoS, quality of service, is implemented on a per device basis with no context of what's called the neighborhood. So that leads in inefficient traffic management. VLANs were introduced to segment traffic and to extend layer 2 networks across the campus environment. We've got link aggregation or bonding, which was developed to increase the capacity between switches over multiple interfaces. But one of the challenges is that we use less than 75% total capacity at times. So all of those drove the need for OpenFlow, for example. We talked about quality of service. Quality of service using OpenFlow is implemented on a per device basis. And we said that that results in inefficient traffic management. OpenFlow, however, has a holistic view of the network, and it knows all of the paths between any 2 points. It can use most of the fields from layer 2 through layer 4, and it allows the matching of headers, and it looks up the path throughout the network. So you can use multiple forwarding means to get better load balancing and processing without being limited to the actual physical topology of the network. Because that controller is a piece of software that we can dynamically program based on the changing requirements of our network, that's where we get essentially the term software-defined networking. So you want to think of defining how your network traffic is being forwarded, much like you would think about creating and identifying your access policies in a firewall. You'll specify the conditions that you want the traffic to match on, such as source and destination IP. You could include wildcards, and then you can include an action to take when you match. With OpenFlow, you define a forwarding policy that's only limited by the capabilities of the controller and your own requirements. So as your needs change, so can your policy change as well. So when we're generally speaking about traffic management, we always want our traffic to go via the fastest or shortest path. But when we have congestion, the fastest or the shortest path can be oversubscribed, and then we need to employ some QoS policies in order to prioritize some traffic over others. With software-defined networking, we can set a policy that prioritizes, for example, time-sensitive traffic over email or bulk traffic, for example. So as that congestion occurs, we can move some of our bulk traffic to a different path and thereby reduce the congestion on the shortest path for our time-sensitive traffic. Question, do you need OpenFlow to manage your network? No. However, can OpenFlow controllers provide some features and benefits that are better than what's available today via your existing standards? Absolutely. When you're using an OpenFlow controller, you can, within its OpenFlow management network, replace most of the management protocols that are running in your existing network. So you don't have to worry about things like routing loops. Your VLANs might even lose meaning. You can use all of your capacity between any of your OpenFlow enabled switches. So you can potentially design your network completely in software and then deploy that with a push of a button. If that sounds like hype, it actually is, because the potential to unlock the power of your network is very real. And the breadth of that power only depends on the capabilities of the controller. And that's why this is such a big buzzword today. And that's ultimately why you guys are here, right? So that OpenFlow controller defines how frames are forwarded through the network, and that controller has an end-to-end view. It can potentially make more intelligent decisions based on the goals that you want to achieve and the capability of the actual hardware, and it can respond to changes in demand as well. And since OpenFlow controls the network, it becomes the central point for anything network related, like your hypervisors, your applications, your security functions, and even load balancing. So what happens is integration actually moves from the individual pieces of hardware to the controller itself. So any device that wants to communicate with an SDN controller has to support the OF or OpenFlow protocol. It's through that interface that the SDN controller pushes down changes to the device flow table that allows you and I as network admins to partition traffic, control the flow of data, increase our optimum performance, and start testing new configurations and applications and bringing those apps to markets a lot quicker. So a forwarding table, for example, would use an IP address or MAC address to decide where to forward that protocol data unit. But a flow table may use the information within the packet to decide the next hop, either an incoming switch port, for example, or TCP port IP address, for example, or a VLAN tag. So a flow is essentially defined as all of the packets that match a flow entry in the switch's flow table. Those entries are pretty general, and they resemble an ACL entry that's found in a firewall, although they could include fields from layers 2, 3, and 4. We have an example on this slide here of the flow table entry that can be manipulated in an OpenFlow switch. This all leads to software-defined networking, where the network is designed and deployed in software instead of hardware. Again, what's the big deal? It allows us to make changes rapidly with fewer configuration errors. We can recover faster from errors. And more importantly, all of the software can signal the network of the parameters that it needs for development, and the controller can set those forwarding policies based on business needs versus technical needs. And then that allows you and I as network engineers or admins to spend more time on engineering and less time tapping on the keyboard using the command line interface. Now we'll talk a little bit about Cisco's application-centric infrastructure. So there are industry shifts that are redefining IT at all levels. We've got on-premise IT consumption models that are shifting to cloud-based services. We've heard of IT as a service. We've heard application as a service. We've got separate development and operations that are moving toward integrated development and operations. We've got box-centric management models that are migrating to application-centric models. So these traditional approaches essentially take a siloed operational view without looking at the common operational model between the application, the network, the security, and the cloud teams. A common operational model will deliver application agility simplified operations, assured performance, and also be able to scale. So Cisco has come up with an application-centric approach to managing your infrastructure devices. Things that might include centralized automation, policy-driven application profiles. Essentially, what ACI does is it delivers software flexibility with the scalability of hardware performance. So some of the things that make up Cisco's ACI are the new Cisco Nexus 9000 series switches. You have the ability for centralized policy management and the Cisco Application Policy Infrastructure Controller, or what they call APIC EM, which we'll talk about in part 2. You've got a Cisco Application Virtual Switch for the virtual network edge. You've got an integrated physical and virtual infrastructure, which provides for an open ecosystem of both network, storage, management, and orchestration vendors, for example. So some of the characteristics of ACI include simplified automation by an application-driven policy model, centralized visibility with real-time application health monitoring, open software flexibility for DevOps teams. You've got scalable performance for multi-tenancy and hardware. And we've talked about how the future of networking with ACI, for example, is about providing a network that you can deploy, monitor, and manage in a way that supports DevOps and rapidly changing applications. So the way that ACI does that is through the reduction of some of our common tasks, and it creates a common policy framework that can automate things like provisioning and managing of resources. So let's talk a little bit about how you might master this, or excuse me, how you might master software-defined networking, or more importantly, how do you master the skills to understand SDN? One of the ways to prepare yourself is to get a good grasp of IP networking and communication protocols. You might consider that a good first step. Traditional networking is good to know as your first step, since it's going to help you to take a deeper dive into software-defined networking. Try to understand network concepts, routing symmetry, understand how TCP and UDP protocols work, the concepts of controllers, flows, different types of SDN vendors that are out there, what type of solutions they might provide for what types of industry. But one of the best ways to learn about software-defined networking, of course, is going to be through real projects. The thing that you might have to keep in mind, however, is that these real-world projects will come from a business requirement that companies actually want to accomplish. So the closer that you begin to look at SDN from a conceptual standpoint, the closer you'll be able to begin bringing your mindset into the world of business. Because there are many things that are out there, but everybody's going to be looking at that from a business perspective, how they can save money, how they can deploy their applications and bring those to market in a timely fashion. So there's a number of ways to interconnect things in-house or using our mobile networks, and many ways to take advantage of all of the different vendors and platforms that specialize in software-defined networking. But at the end of the day, isn't it all about understanding who our customer is, understanding the requirements, and knowing how one packet flows in what form, from where to where, and what happens when one particular controller dies? One of the other recommendations is learn OpenFlow, learn what it is, learn about those northbound and southbound APIs. You might consider picking up a bit of Python and or Java. You might need to understand the concepts of cybersecurity from the standpoint of cloud perimeter protection. Some people refer to it as SDP, or software-defined perimeter. You might include Linux as part of your skill set. There are also other concepts around software-defined wide area network that you also might understand to help you get better familiar with things when it comes to jitter rate and using multiple ISPs. If you are really interested in taking it up another notch, there's a book that I'm familiar with that's called, I believe it's called Transitioning Your Career into Cloud, IoT, and SDN Study Path for Network Engineers. You might want to take a look at that as well. And again, while you are preparing for SDN, don't just think of SDN, think of everything that it has to offer to help businesses and your customer stay connected, and don't think of it necessarily as a specific set of skills. So as you see the explosion of these new technologies and the gradual shift of networking as the future progresses, it's going to be more about not just knowing one small set of skills. It's going to be more about, in my opinion, being a network consultant or systems integrator, as well as understanding and combining a multitude of general IT skill sets. So the daily job of the average network engineer is going to continue to become increasingly fluid over time. And the role of that network admin or network engineer is going to require that we have a broader skill set than we had in the past. And that skill set has to be properly aligned with the business goals and objectives of our customers that are out there. So remember that it's the network engineers and admins that sit at the heart of our network infrastructure. So it's going to require that we have a deep understanding of the applications and the data that are riding across the network. And that's going to be true given the fact that there have been silos of server and storage administration that are being torn down thanks to technologies like SDN that include virtualization, containers, and hyperconvergence. And because the network is the nucleus that binds all of these technologies together, you and I as network admins and engineers are going to be the ones that are responsible for understanding how they integrate from end to end. And unfortunately, the days of you and I knowing 1 through 4 layers of the OSI model are going to be behind us. Today, we've got to understand the entire stack all the way up to and including the application layer. Also, I don't want to stop without mentioning that security, of course, is going to play an increasing role in the daily duties of you and I. It's no longer an afterthought. A lot of times it's going to be the first step in any new infrastructure project that we have. And it's up to us to figure out what the internal and perimeter defenses are going to be in order to provide a solution that's going to include all of the infrastructure devices. And one of the biggest challenges associated with SDN is going to be change. Changing networks means introducing new ideas and ultimately new risks. So as a reminder, what are the skill sets that network engineers need to focus on? We need to learn how to deal with and understand conceptually what are SDN controllers. We need to learn OpenFlow, how to manage the interaction of OpenFlow with those apps, and also how to connect via those northbound and southbound APIs. And if you want to work in the data center where we've been talking about divergence for a number of years, it's going to start with converging our software and networking and hypervisors and role-based management farms. So we've talked about SDN, we've talked about its architecture, we've learned about the role that SDN has in reshaping our network environment. In the future, we're going to talk about some configuration examples of SDN solutions like OpenSDN. We're going to talk about OpenFlow, Cisco ACI, and also Cisco Epic EM. Those are going to be the topics for part 2 on June 12th. That agenda will include introduction to the ACI fabric, understanding the application network policy profiles, how to master the SDN with extensive training, and why register with companies like Netcom, for example, for learning how to deal with and have the skills necessary to participate in SDN. I hope this session has helped to get a global understanding of what SDN is about and why the market is looking for solutions like this. And it looks like we only have a few minutes, but we can certainly open it up for some questions and answers.
Thank you so much, Robert. That was very informative. We'll get back to you with some questions. But first, as we celebrate our 20th anniversary to serve you with the best-in-class IT and business certification training, we bring you an unbeatable 20th year celebration offer this month to make your learning even more fantastic. We're offering up to 50% off on some of our popular courses. Netcom Learning offers a comprehensive portfolio for networking courses that you can see right up there on your screen, so do take advantage of them, as well as our part 2 from today's series. And for all of you attending today, please know that we are sharing the presentation slides so you can see in detail all the networking training courses available by clicking the link on your screen once you get those downloaded. And if you'd like to learn even more about applications of SDN in Cisco and its products, you can register to our June 12th webinar, The Applications of SDN in Cisco, Part 2. Team training can also be customized and accelerated to meet your organization's specific needs. You can contact us today to be connected to one of our learning consultants to help advise you on your specific needs, or email us at webinar@netcomlearning.com, or search our catalog also at netcomlearning.com. And we all know technical skills are necessary to empower our careers, but do you need to improve or upgrade your leadership skills as well in order to accelerate your career? Along with your technical abilities, develop the skills you need to manage yourself, others, and business better. Welcome to Starter Learning, a collaborative knowledge platform bringing the world's best business and leadership insights from Fortune 1000 leaders, best-selling authors, and Ivy League professors. Further, if you are interested in learning from the top American leaders, you can log on to the e-learning platform at starterlearning.com and avail the special promotion meant for first-time users. Use your coupon code SARDER10 and begin your leadership journey now. And right now we are going to be launching a quick poll to find out how many might be interested in taking some additional training. So please just take a few minutes to fill that out so you can take advantage of all that Netcom has to offer. In addition, we do have a lot more informative webinars coming up, and you can go to netcomlearning.com/webinars in order to register. And don't forget to like and follow our social media pages to get the latest technology updates. You can refer to the GoToWebinar webinar chat windows for all of our links right up there on your screen. Okay, so are there any other final thoughts, Robert, before we have to end today's session?
Not offhand. I just wanted to thank everyone for their participation, and it was my pleasure to be of service. And if you have any questions, Tracy will certainly collect those, and we can get back to you and answer those questions. And I appreciate everybody's time this afternoon.
And sadly, we are out of time, but thank you, Robert, and thank you all for joining us today. If you do come up with any additional questions, feel free to send them to webinar@netcomlearning.com at any time. We hope that you found today's webinar informative, and we look forward to seeing you back here with us soon. Feel free to tell your friends and colleagues about our webinars and other courses. Have a great day, everyone.